Thank you for being here with us. So good afternoon. This is the afternoon second session. And this session, we have 5 talks covering classical problem in causality, including mediation analysis, estimation heterogeneous causal effects, general kind of causal inference problems, and how to learn latent variables in the causal structure. So our first speaker is Professor Hui Li. Professor Hui Li is from Renmin University of China, and the talk is about sparse mediation analysis with unmeasured mediator-outcome confounding.
Thank you for the introduction. Today, I would like to present our recent work, sparse causal mediation analysis with unmeasured mediator-outcome confounding. This is a joint work with Dr. Shuai Kang, Professor Liu Lan, and Professor He Yangbo. Okay, I will first talk about what is mediation. Mediation analysis helps to understand not only whether a treatment can impact a certain outcome, but also how it impacts the outcome. So the standard paradigm in mediation analysis involves three variables: a treatment, an outcome, and a mediator. So a mediator is a variable that is intermediate in the causal process relating the treatment and the outcome. So in this genetic example, the genetic variance is the treatment, the lung cancer is an outcome, and the smoking is a mediator. Mediation analysis enables us to decompose the total average causal effect into the direct effect and the indirect effect through the mediator. So in this genetic example, mediation allows us to investigate how the genetic variance and the lung cancer are related. Specifically, the genetic variation predicts a higher risk of lung cancer because genetic influences addiction to smoking, which in turn increases the risk of lung cancer. So mediation analysis was first proposed with a single mediator using linear structural equation models. So this is a classical paper by Barry and Kinney in 1986. So this framework often involves 2 linear models. The first is a linear model for the outcome with treatment Z and the mediator M as predictors. And the second is the linear model for the mediator with the treatment Z as a predictor. So in these 2 models, the coefficient beta 1 is the direct effect of the treatment on the outcome. And the product of the 2 coefficients, gamma 1 and beta 2, is the indirect effect of the treatment on the outcome through the mediator M. And recent advances have extended the mediation model to the setting of multivariate or high-dimensional mediators due to the increasing availability of measurements on a larger number of potential mediators. Classical mediation analysis relies on sequential ignorability assumption. Roughly speaking, it often requires no unmeasured confounding among the relationships of Z and M, of Z and Y, and M and Y. So, however, this assumption may be not plausible in practice because even in randomized experiments, the treatment Z is randomized, but the mediator is not randomized, and hence there may still exist unmeasured variables confounding the relationship between the mediator and the outcome, such as the unmeasured variable U in this causal diagram. So mediation analysis under unmeasured confounding is challenging due to identification difficulties. And identification can be achieved by leveraging some observed auxiliary variables that satisfy certain exclusion restrictions, such as instrument variables or the negative control variables. However, these auxiliary variables often satisfy certain stringent assumptions, and they are often not easy to be found in practice. So without these auxiliary variables, the interaction between baseline covariance and the treatment may be used as instrument variables for the effect of the mediator on the outcome. When the outcome model follows some special term, for example, the linear form, and this is a classic paper by Tenheb and al. In 2007 biometrics paper. And Fulcher et al. 2019 proposed an alternative identification strategy by leveraging heterogeneity restriction on the observed data. So most of these methods focus on the case of a univariate mediator. And similar methods can be used in settings with multiple mediators, simply treating them as a single vector valued mediator. So these two are very interesting papers. First is by Professor Zhou, JRSSB paper, and the second is from Baoluo Sun. When there are many or even high-dimensional mediators, active mediation pathway selection is also an important but challenging problem. So there are many methods that have been proposed to tackle with this issue. For example, Zhang et al. Proposed a regularized penalty approach for the outcome model after sure independent screening of mediators, and so on. So all these measures assume the absence of unmeasured confounding. So failing to adjust for unmeasured confounders not only induces biased estimates of the direct and indirect effects, but may also lead to ignoring important mediators. So in this paper, we propose a strategy to address both identification and mediator selection issues in the presence of unmeasured confounding under the structure equation modeling framework. Now let me introduce the additional notations and the proposed model. So besides the treatment Z, the mediator M, and the observed outcome Y, we let X denote the observed covariates and let U denote the unobserved confounders. So let G of Zx denote the regression mean of the mediators on treatment and observed covariates, and let zeta denote the corresponding regression residual. So we propose the following structural equation model with unobserved confounders U. It basically involves the following two models. The first is a linear model for the outcome Y with the treatment Z, the mediator M, the observed covariates X, and unobserved variables U as predictors. And second is a linear model for the regression residual zeta. It only involves unmeasured variables U as predictors because zeta is a regression residual, so it is uncorrelated with the observed treatment and covariates. And so Z and X do not appear in the second model for zeta. And actually, we require the second model to be a latent factor model. So this basically requires the mediators do not affect each other. And and without loss of generality, we assume U has been standardized with zero. Okay, with zero mean and identity covariance matrix, and following the standard latent factor model restrictions, we restricted the covariance matrix of the error term to be diagonal. So under the above two models, for binary treatment Z, we have the direct effect is exactly the coefficient beta 1 is the outcome model. And the total indirect effect through all mediators have this form. So here beta 2 is the coefficient of the mediator M in the outcome model, and this term is the causal effect of the treatment on all mediators. And specifically, the indirect effect through the JSON mediator can be expressed as the product of beta 2J and this one. So this one is the JSON component of this expression. So from this expression, we have expressed the effects of interest as functions of beta 1, beta 2. So we only need to focus on beta 1, beta 2. And we denote beta to be the vector of whole of all coefficients in the outcome model. A direct regression Y on the observed variables Z, M, and X using such as OLS often leads to biased estimates because U is correlated with the mediator M. So our first question is how to identify beta, right? So intuitively, if we have removed the correlation part from U, then we may achieve the identifiability of beta. So in this slide, I will discuss the identification idea. The tools of projection enable us to decouple the correlations between U and M. or equivalent between U and the regression residual zeta. Specifically, by L2 projection, we can choose some projection matrix data such that this equation holds. And this term, delta transpose zeta, is actually the projection of the Unmeasured confounding U onto the space spanned by zeta. And based on our latent factor model, we have the following expression for the projection matrix delta. And we can see that delta actually depends on unknown parameters, namely the factor loading gamma and the covariance sigma epsilon. And we then define the linear projection L. We then use L to denote the linear projection, and psi to denote the combinations of some error terms. This term is a projection error, and eta is a error term in the original outcome model. So using this newly introduced notations, we can rewrite the outcome model as follows. So here, psi is an error term, and we can show that psi now in the new outcome model is uncorrelated with all predictors, including Z, M, X, and L. So if L were known, we can use many methods to achieve the identification and estimation of beta. But unfortunately, here L depends on unknown parameters. So we need to carefully study the identification and estimation of beta. And we also found that comparing this new model with the original outcome model, we found that L has replaced the unmeasured confounding U in the original model. So here L can be viewed as some proxy variable of the unmeasured confounding U. Okay, so this is our first result about identification. This specifically is the vector parameters beta 0 to beta 3 is identifiable, but beta 4 is identifiable only up to some rotation. So what is beta 4? Beta 4 is the coefficient of the unmeasured confounder U in the outcome model. So its identifiability depends on some rotation. This makes sense because this is the coefficient of measured variable. Of course, our identification requires some conditions. The first is a standard requirement for identification in factor analysis, which guarantees that the factor loading gamma is identifiable up to some rotation. And the condition 2 requires some full rank matrix condition. It essentially requires mediator models containing some nonlinear terms of treatment and baseline covariance.
Recording in progress.
As reviewed earlier, such nonlinear terms is instrument variables for the effects of the mediators on the outcome Y. So interesting JRSB paper by Professor Zhou made similar identification conditions in the presence of multiple mediators. However, comparing with their paper, our approach only needs one of the mediators to contain some nonlinear terms. But their approach requires all mediators satisfying such restrictions. So we have actually relaxed their assumption because we have utilized the latent factor model structure among the multiple mediators. So I will talk about the estimation procedure, and for simplicity, we specify some parametric model for the mediators indexed by a finite dimensional parameter gamma, and let zeta of gamma denote the corresponding regression residual. So the estimation procedure is summarized as follows. In the first step, we aim to obtain an estimate of the regression residual. So we first solve the minimization problem to obtain an estimate of the parameter gamma, and then obtain the estimated residual zeta of height gamma. And in the second step, we implement a factor analysis on the estimated regression residual zeta of height gamma to obtain the estimated factor loading and the estimated covariance matrix, and then obtain the estimated the projection matrix had delta, and finally obtain the estimate had an error of the constructed proxy variable error. So after obtaining these estimates, we in the third step solve the following adaptive lasso problem to obtain an estimator at beta AD. So in this problem, it involves the loss function term and the adaptive lasso penalty term, and different from the classical adaptive lasso problem. Our problem is more complicated. The reasons there are two reasons. The first is that here in the loss function, an estimated variable error is included, not the predictor itself. And in second difference is that we only partially penalize the beta 2 instead of the whole vector of parameters. So although with such complexities, we can still achieve the oracle property of our proposed estimator. Specifically, under some regulatory conditions, we have the following two results. The first is the consistency in variable selection. It means that the estimator identifies the true non-zero covariance of beta 2 with the probability asymptotic approaching 1. And second is the asymptotic distribution of the estimator is the same as if the true underlying subset model were given in advance. Okay, next I will talk about how to consistently select active mediation pathways when there are multiple mediators. So here is a causal graph showing the multi-mediator structure with unmeasured variables U confounding all mediators M and the outcome Y. And so to consistently select the active mediation pathways when there are no unmeasured confounding U, traditional approaches often conduct multiple testing with a composite null hypothesis for each mediator G. That is, they test whether the product of llama J and beta 2J equals 0. Here, llama J is the effect of Z on MG, and beta 2J is the effect of MG on Y. So their product is the indirect effect of the treatment on the outcomes through the mediator MG. For example, in yesterday's talk by Professor Xihong Lin, they consider a similar problem, and they conduct such a testing with a composite null hypothesis. But in practice, this is very complicated because the composite null hypothesis involves three different cases. Namely that either of these two parameters is 0 or both of them are 0. So in this paper, we propose an alternative two-step procedure. And in the first step, we obtain the index set from the non-zero covariance of the estimator. So this estimated index set is actually the estimated set of mediators that have non-zero effects on the outcome Y, right? And due to the oracle property of the proposed estimator, this estimated set is approximately equal to the true set of mediators that have non-zero effects on the outcome Y. And hence, to select the active mediation pathways, we only need to find from those selected mediators that have also been affected by the treatment. And hence, in the second step, we only need to test whether llama J equals 0 among those selected mediators in the first step, right? And here, llama J is the effect of the treatment on the mediators. And so this here is a corollary showing that our proposed two-step procedure can consistently select the true active mediator set with high probability. So here, alpha J is a significance level in the hypothesis testing of our second step. So if we set alpha J to be alpha over H, where H is the number of selected mediators in the first step, then we essentially use the bond-friendly correction method to control the FWER at some given significance level alpha. But this method may be conservative when H is large. So one can use other more powerful techniques such as Holmes method or Hotberger's method or even the BH procedure that is used to control FDR to adjust the multiple testing issues, right? 3 minutes, okay. I will skip the simulation studies. The simulation studies, I can tell you that simulation studies demonstrates our proposed approach well. So I will skip these details. And here is mouse obesity data that we use to illustrate the proposed approach. This data set was described by Wang et al., and they concern the effect of gene expressions on the body weight of mice. The SNP called this name was previously identified to be strongly associated with body weight and adiposity. So here we analyze how it affects body weight directly and indirectly through gene expressions. The data we used include 287 mice and 165 gene expressions, which are regarded as potential mediators. And the estimate of the direct effect is 0.25 and with p-value pretty large, implying that the SNP does not directly affect the outcome significantly. The naive adaptive lasso method shows similar results with positive estimate and non-significant p-value. This table shows the estimate of natural indirect effect of select genes, standard deviation, and corresponding p-values of individual mediation pathways. So as introduced earlier, our proposed procedure involves 2 steps. In the first step, we aim to find those mediators that have non-zero effects on the outcome. And so in this example, we have selected 27 genes. And in the second step, we use hypothesis testing to individually test whether the SNP affects those selected 27 genes. And using Bonferroni correction, we found that these 2 genes are significant. So this also confirms findings in previous studies. Actually, we also use other more powerful techniques such as Bonferroni, such as Holmes method or BH procedure, but the results are unchanging. So this shows that these 2 genes are pretty strong active mediators among between the SNP and the outcome. Okay, so here is a summary of my talk. This paper provides identification and selection of active mediation pathways and Unmeasured confounding based on identifying multiple mediators. And there are some future work to be considered. Firstly, the asymptotic results are established for fixed dimension PL mediator in this paper. And it is of interest to investigate the theoretical properties when the dimension P grows with sample size N. And the second is that our approach relies on standard latent effect model, allowing unmeasured confounding U to affect all mediators, but also requiring no edges among all mediators. So the identification results may be extended to handle causal order mediators using other variants of latent effect models. Okay, thank you, everyone.
Thank you very much, Professor Li. So we have time for one quick question.
Thank you. Very interesting. I guess it is correctly understood that you are not able to identify this non-parametrically. So you are identifying through essentially a functional form assumption. Yeah. How worried should one be about that? And is it at all testable? I guess the answer is no.
Yeah, right. You are right. They say that we have imposed a linear outcome model in this presentation, but we can relax this outcome model a little bit. For example, we can include some more interaction terms between the treatment, the mediator, and the observed queries. And but for the moment, we are still hard to obtain non-parametric identification due to the unmeasured confounding. Yeah.
Great. Thank you very much. Let's thank our speaker, Professor Li, once again. Thank you.